Hello. Thank you, everyone, for coming in today. It's wonderful to have you all with us, and this is the last keynote of the conference. This is my pleasure to introduce you to Dr. Judea Pearl. He's a Chancellor's Emeritus Professor at UCLA and the winner of 2011 Turing Award, also considered the Nobel Prize of Computing. He's best known for championing the probabilistic approach to artificial intelligence and the development of Bayesian networks. So I'm handing the mic now to Judea. Give him a huge round of applause.
Thank you, Abby. Thank you. Can you hear me? Good. I'm a little late, so I'll try to be as concise as possible and convey to you the essence of my talk here in the very first slide. I have a proverb which I composed in the car service coming here. I think that will summarize it very clearly. My message is very simple. It is that data is our window to reality, and data science is the eyeglass that enables us to look through the window. It is not a mirror through which data looks at itself under makeup. That is the essence of things, which means that data science is a two-body science, connects data and reality, interpret reality in view of the data. Well, you can say we all know that. So let's go and see what has been done with data science thus far. And my outline will be, one, why data science needs a new engine to answer causal questions. I call it a new engine because for us computer scientists, a piece of software is an engine. And I call it a new engine because it is a new organ in our mind, one that has its own logic, its own unique features, and one that we haven't even been aware that we have it. Like a guy finds out one day that he has or she has a liver. We can live our life without knowing that we have a liver. But once we discover that, that the liver is there and its function, then it's the duty of the physician or the physiologist to understand the function and to be able to repair it when it goes wrong. So I'm going to talk about the structure of this new engine. I don't want to keep on saying liver. And the two fundamental laws of causal inference, you can look at it as a double helix, because once you see and you acquire and you commit yourself to these two fundamental laws, you don't have to listen to any lectures like this one. You can do everything yourself. It's derivable mathematically. That's a nice thing about science. Sometimes you get the key, and the rest is derivable, like the axioms of geometry. And then I'm going to spend the second part of my talk convincing you that it is not just a mathematical gimmick, but it has application, and I will convey the application through a list of 7 pillars. These are tools that you would be able to do once you acquire the double helix. And these are tools that go beyond data science. These are tools that enables you to answer questions that ordinary statistics cannot answer, that ordinary machine learning cannot answer today. They will tomorrow. And it has revolutionized data-intensive sciences, from epidemiology to economics to social science. Okay, let's start with the causal model and why do we need to have one. something happens 10,000 years ago. Human beings accounted for less than 0.1% of all vertebrate life on planet Earth. And today the percentage, including livestock, increases 98%. You can argue with the numbers, depends if you count the chickens or the goats, but the basic fact is that there has been a super evolutionary development by which human beings were able to dominate the planet. There's no denial that something happened and it's super evolutionary. No other species has attained this kind of global dominion, and we haven't seen any such transition throughout the planet's life, throughout the evolutionary process. It's unique. So what happened? Well, there are many theories, but the one that appeals to me as a computer scientist who asks not what happened, but what computational facility did humans acquire 10,000 years ago that they did not possess before. That is a secret which we want to grasp, and equip machine with. And the one that appeals to me most is here. This is the secret of the Homo sapiens, our ancestors, which enabled them to migrate from Africa and essentially wipe out the Neanderthal men in Europe and wiped out the Homo erectus in Asia and dominate the planet. What did they have that the Neanderthal man did not have, even though physical capabilities were in favor of the Neanderthal man in terms of size and other abilities? Well, look at that. That is called the Lion Man of Statel Cave. Was found in Germany, southwest Germany, in a cave. And it's the first artifact that describes an object that does not exist in the physical world. It's a combination of a lion head and a human body. You can see it here, miniaturized. The ability to imagine things that do not really exist, that was the secret by which I didn't invent the theory. It's among the prevalent theories of anthropologists. I took it from Harari's book, Sapiens, where he claims that this ability allows man to develop larger society. How? By developing a market for promises. If you can imagine things that don't exist, then I can promise you things that do not exist. And if you trust me, then we form a coherent society that can work in unison and form villages and cities and empires, and you know where we are today. Larger society working in unison. Because the village elderly could offer the farmers a promise. For instance, a loot. Once we conquer the next village, okay, that's a promise. The ruler of the country could promise its subjects protection and larger loot if we win the battle against the neighboring country. And the priest could offer its parishioners, an afterlife and all the good things that you ever wish to. And that amounts to trust. It amounts of marketing. For that, the ruler required that you send your sons and daughters to serve in his harem or in his palace. It's a sacrifice, but the promise made up for it. So Harari says It's unique to human. You can teach monkeys all kinds of tricks, but one thing you cannot teach monkeys is to convince a monkey to give you a banana by promising him limitless banana after death in monkey heaven. Okay? And people do go for that. We know. So it's unique to human. And it required a special computational facility to imagine the result of the promise, the accomplishment, the fulfillment of the promise. Okay? And I'm going to causal question. That allows us not only to engage in dreams about the afterlife, but also to do things that are practical. For instance, we could answer causal questions of the following type. How effective is a given treatment in preventing a disease? Was it the new tax break that caused our sales to go up, or our marketing campaign? Many of you are engaged in electronic marketing. Okay? It's a crucial problem. And what is the annual health cost attributed to obesity? It has been in the New York Times in the past few months. Okay? Is it obesity that kills, or the soda? Can hiring records prove an employer guilty of sex discrimination? I'm about to quit my job. Will I regret it? Personal decision making. Okay? Notice that I marked certain verbs here in yellow, and those are the keywords. I can recognize them from 10 miles away. I trained myself to look at the causal attributes that define a sentence, that define a question, which make it uniquely part of our liver, okay? That you cannot express in any other language except the language of causation. Preventing, causative, of course, attribution, discrimination, and regret. The interesting thing about them is that they could not be articulable in the standard grammar of science, which means that until 3 or 4 decades ago, not only he couldn't answer them, he couldn't even put them on paper. He couldn't put on paper a simple fact that a rooster crow does not cause the sun to rise. There's correlation there, but we know that the sun doesn't care about the rooster crow. The rooster crow comes before the sun, and they're highly correlated. We all understand that it is not the rooster that causes the sun to crow. And we cannot write it down in mathematics. And if you cannot write things down in mathematics, something happens. You can talk about it, you can teach your children about it, you can convince your friend that it's not the rooster that could. You can convince them, all in heuristics and in the verbal level, but you cannot combine it with data. To be combined with data, all these notions about cause-effect relationship must have a mathematical form. So you can tell whether you have enough information to harness the data and get quantitative answers to, for instance, to what degree does the treatment prevent a disease? Okay? How can we find from data whether the employer was exercising discrimination, sex discrimination in hiring? Can data tell us that, and how? That requires mathematics. And what science has given us, unfortunately, is a language which is symmetric. A language is built upon algebra. And algebra is built upon a connective called equality sign. It's right here. I put the blame on this fellow, see? Equality is symmetric. If y is equal to ax, then x is equal to y over a. Okay? So the whole study of algebra that you learn in high school by which children learn physics and geometry and optics. It's all very nice, but it doesn't answer the liver. The engine, it doesn't allow you to turn the engine off, the engine of causation, and answer simple questions like that. You cannot even articulate the question in that language of algebra. Well, the replacement for that has been an arrow. For us computer scientists, an arrow is not a new animal. An arrow is an assignment operator. It means that if we have that nature is a society of listeners. Okay. Variables, every variable that we see around us, listen to other variables and assign value to itself according to what it hears. For instance, if I give you an example, if this microphone is at 23 degrees centigrade, okay, I envision that this temperature is determined by nature after looking at all the neighboring variables, the radiation from this light bulb, okay, the speed of the molecules coming from your mouth or my mouth, okay, taking them into account and accordingly assigning a value to the temperature here. Is Y is assigned a value according to what nature listens and hears from X. You can have vectors and all these kind of things. You can have matrix. But basically, there is a fundamental difference between equality sign and the assignment operator. Today, we express it in the form of a graph. So the graph is nothing else, but the arrow here is simply expressing the idea, the metaphor of a society of listeners, okay, by which every variable assigned to himself or herself a value according to what it sees in the neighborhood. Okay. It's a complex process. You know, to determine the process of, I wouldn't envy nature for needing to decide what temperature this microphone has. You know, so many variables around. But the mere imagining that this is what goes on in nature allows you to liberate yourself from the handcuff of this equality sign, which is totally symmetric and doesn't allow you to express all these nice verbs. I'm going now into the ladder of causation. But this is a theoretical hierarchy. It comes from theoretical analysis of what you can do with the arrow that you could not do with the equality sign. It leads to a hierarchy of complexity in the sense that you can answer question at level I only if you have information from level I or higher, which means right here you have associations, statistics, seeing, observing, passive seeing, hand off. Okay? Astronomy, for instance. Okay? Hands off. You cannot move the stars. Okay? And you answer questions such as, what if I see? How would seeing X change my belief in Y? You're all familiar with it because you're data scientists. Okay, this is what data science is today, and that is why I put the robot here on level 1, together with the owls, because this is what owls and eagles and snakes have excelled in, developing through millions of years of evolution an optical system that we cannot even duplicate in the laboratory. So sophisticated it is. And however, eagles and owls have not developed eyeglasses, nor microscope or telescope. Okay? And we did. And only in the past 3,000 years. So I'm heading here. And I'm saying AI should really aim at climbing this ladder and be able to have an automatic scientist. Your robot should be smart enough to become, in a way, in a small world, but automatic scientist, one who can invent things, one who can decide what experiment to write at any given time to conduct, and so forth. So let's go over the ladder. First level, we have association, statistic. What does a symptom tell me about a disease? What does a survey tell me about the election results? Okay, I see something. What do you tell me about my belief in something else? Easy. That's what we are doing it every day of the year. That's statistics, and this is data science the way it is practiced today. The next step is to answer intervention question. For instance, what if I do? A derivative, a cousin of that will be how. Once you know the effect of your actions, then you can answer how do I get what I want. Okay? For instance, if I take an aspirin, will my headache be over? What if we ban cigarettes? Okay, so cigarettes, you know, have never been banned before successfully. There's no means by which we can educate children or adults to stop smoking or force them to do that. But we can stipulate what the effect is going to be. We can argue whether there's going to be a black market of smuggling from Canada and so on. We can talk about it, and this is part of our ability, part of level 2, to stipulate the result of your actions, actions which you have not even experienced before. The next level is counterfactuals. What if I did things differently? So I actually worked, and I took an aspirin, and I asked, was it the aspirin that stopped my headache? I go back in time, I do introspection, I do an exercise of imagination, like the lion head, like the lion man, and I imagine things that do not exist. I just rerun history and re-simulate my system. And I ask, would I be better off? Would Kennedy be alive if Oswald had not killed him? What if I had not smoked in the past 2 years, and many other counterfactual questions? Now, some people say, who cares about the past? I want to improve life here on Earth, so I want to answer only interventional questions. Now, you do have to ask counterfactual, because counterfactual, number one, is a very effective language in order to convince you to modify your software. If you would have been better off acting differently, then you would think about what is it about in my software that forced me to act the way I did. And you are the one that knows your software, and you are the one that says, okay, let me change this module. And next time I'm facing a decision in the heat of soccer game, okay, I'm going to pass to X instead of Y, because this opportunity calls for doing that, and the software piece that caused me to pass to Y instead of X needs to be modified. So it's a very effective way of luring agents to change their internal software. That is a hierarchy very important. I'm surprised that before my book, Book of Wine, came out, so many people did not know about the hierarchy. And they write to me and they say, wow, it's an eye-opener. It's exactly what I was facing, or it's exactly the way it guides my thought. Because I had difficulty working in level I, I didn't have information from level I plus 1. Okay? Keep it in mind. Some people say it's an eye-opener. For me, it comes from the mathematics. I can prove it. You cannot do things in level I unless you have information from I plus 1. So it comes from the mathematics. It wasn't something that was discovered by surgery of our mind. But it turns out if the mathematics tell you they cannot do something, then it's a different species. Right? It requires, and it did. This level has a this level has a different logic than this level. This is a level of correlation. And this is a level of intervention. And this is a level of counterfactual. They have a different logic to them. You cannot derive the conclusions of these levels from ordinary logic, from standard predicate logic. No, they require a new internal semantics and syntactics and derivation. So let me go and see an example of where the logic of causation conflicts with the logic of correlation. And the easiest way to convince you that there is a conflict there is that one. It's Simpson paradox. Here is the data that you might well obtain in your laboratory when you plot a scatter plot of cholesterol level versus exercise. So if you look at your overall population, you find that the more you exercise, the higher the cholesterol level. It doesn't gel with what we read in the New York Times. So there is something there. If you look, however, in every age group, you find what you expect, that the more you exercise, the lower your cholesterol level. Okay? And this is just an artifact coming because you aggregate data that should not be aggregated. Okay? So it's known as Simpson paradox. It exists since Pearson discovered that in 1898. And he just said, this is spurious correlation, don't pay attention to that. Anyone who thinks that correlation is causation is wrong, done. However, for us computer scientists, it's not done. It ought to be seriously addressed. Because the next question is, so which data should we trust? Imagine that you are a robot. You are not a New York Times reader, so you have a choice here between trusting that kind of data or that data. Well, some of the answers, I mean, the statistician says, I should trust that, of course, because it's more specific, right? And the decision maker, you have to decide whether you recommend exercise or not. Why would you trust that instead of that? Well, the normal answer is more specific. Is it true? It turns out it's not true. There are cases where the real answer and the correct answer lies in the aggregate data, not in the age-specific data, not in the C-specific, if C is a set of covariates that you can measure, but lies in the aggregate. For instance, if this was a blood pressure after treatment, you would not aggregate according to people's level of blood pressure, nor you would do it if, well, there are many examples where it flips around. So the question is, you are a robot, and you have to advise the decision maker what to recommend. What is the criterion? What about seatbelt usage? Would you classify people by their seatbelt usage? It turns out if you do it, you get the wrong answer. So we need to have an algorithm that will tell us what covariates that we should consult before we come up with the correct answer. Where is it? Where is the answer hidden? It's not hidden in the data. It takes something beyond the data. It's hidden in your model of the world. There's a difference between seat belts and age. Right? One affects your outcome, the other one does not. A drug doesn't change your age.
Microphone.
Say it again?
Your microphone.
Oh, I'm sorry, so sorry. Oh, you can see that I'm a professor. I teach small classes. Oh, I'm so sorry. So which word did you miss? Seat belts, right. Well, it's not a theoretical discussion only. It's becoming quite practical because, you know, in Europe, they are talking about legislating what they call DTRP, right? Or PR. Data, general data regulation. What's the piece of it? Protection regulation, yeah. Which gives every individual 3 rights. A right to know, number one, the right to know whether an automatic algorithm participated in a decision that affects that person's life. Second, the right to challenge that decision. And third one, the right to explanation of why the decision was made. So here is a hypothetical dialogue between a loan requester and the machine. I demand an explanation for why my loan was denied, and the answer is because you are a female. First of all, it's forbidden because there are some attributes which are forbidden to be even to take part in a decision, like sex, religion, race, and so on. But aside from that, let's see how Simpson paradox plays tricks on us here. And what if I was a male? It would be denied too. Come on, so who's getting a loan here? Okay. Those who do not divulge their gender. This is exactly what Simpson paradox tells you. Okay? You have a drug here which is good for men and good for women, but it's bad for a person. This is the logic of correlation. You can find in a correlation a triplet of that nature, that a trend, 15 minutes, I can't afford it. I'm going to go right to the 7 pillars. Okay, I'm glad you're mine, okay? But you can see the tricks here, okay? The logic of correlation accommodates it and forgives that it happens in a correlation domain. It doesn't happen in a causal domain. It's a different logic. Your intuition rebels against the idea that you have a drug, a magic drug, that is good for men, good for women, and bad for a person. And that is not derivable for common logic. Definitely not from correlation, but not even from Aristotelian or Boolean logic. That's something unique to the logic of causation. So it has to be incorporated into the European regulatory system, correct? What is the logic? The logic is built on something very basic. It is the difference between acting and seeing. And here is a simple story, rain and slippery, wet. Seeing a sprinkler on gives you different information than turning it on. Turning it on means that you have to cut off all relationship between the sprinkler on and the sprinkler and the season, which previously controlled the sprinkler. Now you are turning the sprinkler on, which means you are exercising your muscle and disable whatever influences made the sprinkler on and off before your intervention. Right? So it's a very simple operator. So by seeing the sprinkler on, I can make inference about the season. By turning it on, I cannot make inferences backward. That's a basic difference. Okay? So all the things that we learn from correlation are going to be changed when you are doing things. So we need the calculus of doing. Okay? And the counterfactual, it belongs there because counterfactual is just doing things after you update the history. You see what you have in your world, pavement is slippery, you update what you know about season, and then you do the surgery. I call this surgery, and this is one of the most important operators in the new algebra of causation. You take equations away. Okay, simple causation, and this is, now I'm going to go to the DNA. Okay. There are two basic laws, fundamentals. If you acquire them, you can fire me. You don't need me anymore. Everything that I've done can be derived by pure algebra, or algebra of causation. So, first one is that if you have a complete model, I'll show you what a complete model is of the universe, about how a variable listens to its neighbors, you can generate all the counterfactuals, simply doing the surgery. With counterfactual, y sub x, the value of y, had x been small x, is nothing else but the solution for y in a model where you perform the surgery over x. Easy. Every high school kid can compute counterfactuals easier than he or she can compute the derived construction in basic geometry. Okay? The second one is, I'm really out of time, that you have a law of conditional independence, which means that separation in the model, the graphical separation, implies that you have conditional independency in the data. Which means that the model tells you what you should observe in the data, which means the data tell you which model is incompatible. And it allows you to do all kinds of nice things because you have first a connection between the causal world and the data world through the deseparation criteria. So just to tell you what it enables you to do, if this is your model of who listens to whom, behind the model there is a functions. But regardless of those functions, just look at the model. Every time you see a missing link, a missing arrow, oh, I'm talking again. Sing with me. Okay, so yeah. Every time you see a missing arrow here in the model, you know there is a conditional independence in the data. Here is one, bing, missing. I can tell you without even knowing those functions that this hole in the data. C and W are independent given the separators S and R. And there's a twist about collider here. Here's another missing arrow. So you know that S and R are independent. Okay. Once you know C, not W, for a reason that I will skip now, it's called a collider. But once you learn that, chick-chock, you can look at the model and decide what you ought to expect in the data. That gives you a way to go back. Good. So from this you can do model testing. From this you can do structural learning. From this you reduce scientific question to adjustments just. What variable should I put here behind the conditional bar? Here, behind the conditional bar, so that I will be able to get the result that I want. Now, what result do you want? This is the engine. You want to answer your query. You don't want to find the mean. You don't want to find confidence intervals. This is not your question. Your question is query. It's a causal question. Like, does the rooster cause the sun to rise? It's causal. But now you have the means of articulating it mathematically, right? Okay, so ask it in the language of counterfactual. Would our sale go up had we exercised a different marketing strategy, a counterfactual? Ask it here, and then answer the theoretical question whether you can find the answer coming from any data that is compatible with your model. Turn the engine, and the answer will come out on a silver platter. So this is how it goes. Here is my query. I want to find the probability of the outcome given that I do X. I take an aspirin, right? I need to have assumptions in a graph. This is your perception of nature. The engine delivers to you a formula. A formula is a recipe. Oh, you want this query? This is your assumptions? Thou shalt take the conditional probability of y given x and z and average it over z. That's a recipe. Okay? And then goes the estimator, and everything that you learn in statistics comes after that. But first you have to express your query honestly. Don't be deterred by the fact that you have the new operator. Your queries are about a new operator, counterfactual and intervention. Ask them honestly, because you have the language, and the engine will help you translate your language to procedures on the data. Okay, I'm going to go now to the pillars. This is what, if you are interested to apply them in practical domain, this is what you do if you just make one little allowance. Be honest. Ask your query, ask the real query that you are really interested in estimating. And second one, be honest about what you perceive to be in the real world in the form of qualitative, who listens to whom. Right? And this is what you can do. I'll jump right away to confounding, counterfactual, algorithmization of counterfactuals, mediation analysis. Since I'm out of time, I will not show you the marvelous things that you can accomplish. They're in my paper and in the book. Okay, each one of them is a result of mathematics and gives you an algorithm for answering those questions. For instance, I want to find the external validity or sample selection via, okay, I'll jump to there, okay? So allow me to go 1, 2, 3, 4, 5, 6, 7, because this is important. In machine learning, you keep on having, first of all, you can send a guy to jail, okay, by looking at the data and deciding and finding out that he had a probability 1 for being guilty. In this case, was it was that the client would have been alive had he not taken the drug. So the drug manufacturer is responsible for that. Okay, it's in the data. So let me go back to what you want to accomplish: direct and indirect effect. Also important because liability depends on direct responsibility versus indirect responsibility. And I like this because in machine learning you can find this problem appearing again and again, and no one has a solution to that. Just a lot of talks, yes. But the machine trained in one environment finds that environmental conditions change Now, when and how can it amortize past learning to the new environment? Okay? So a robot is trained in the cockpit, and now he has to exercise in the battlefield. Things have changed, of course. And what can be amortized from previous learning? Okay. Now, this problem, it has a complete solution mathematically. If you only tell what you suspect to have changed, and on the graph, put down areas of suspicion, okay? And it allows you to do things like that. For instance, combine data from various sites, various hospitals, various studies, each conducted under different conditions, under different populations, okay? And answering the questions about should the guy go, or should we recommend operations to some guy in Arkansas. And I've never been to Arkansas. I don't know if you've been there, but how can you stipulate from studies, diverse studies, on crazy conditions? Here there were volunteers, and this randomized controlled trial. Here there were college students. We know the college students do not act like typical members of the population in Arkansas. Okay? So how can we put it all together and come out with a query? The query was, should we recommend operation or surgery to a guy in Arkansas? Okay? This way it's hopeless. But if you reduce it to graphs, then it becomes hopeful. The specific characteristics and the idiosyncrasies of each study can be represented in the graph with various gimmicks here. Yeah, 2 minutes, terrific, enough for me to finish with an anthem. it's okay, I'll get there. Okay? And once you have it encoded in the graph, there is an algorithm that will take all this graph, put them together, and answer your query. And the algorithm is complete. Now, that's something that people don't get. Complete means that if it tells you no, you can't do any better. You don't have enough information. And once you have a no answer, you can ask, so what do I need to assume to get it through or to get the answer? The system can recommend to you. If you can only measure something that stands between this and that, then I'll be able to answer the question. Okay? So this is what completeness means. Don't miss it. So anytime people talk about transfer learning, this is what transfer learning is. Missing data, I'm sure you're not faced with that problem. But it's also, we have a solution for that. It turned out to be a causal problem because there are reasons why data is missing. It's not something that is in statistics. Statistics doesn't tell you why the data is missing. Once you incorporate it, you have a nice algorithms and you can answer nice questions. Yeah, I'm going so quickly. Look at what the wonderful things you're going to miss because you're not giving me another answer here. And nope. Good, I finished the missing data. And the next one is causal discovery, which I'm going to just summarize quickly. What asymmetries in the data gives you hints about the structure of your model. It's growing field. And I'll finish it by saying, you see, I got to the conclusion before people throw tomatoes at me. So, yeah. More has been learned about causal inference in the last few decades than the sum total of everything that has been learned about it in all prior recorded history. It's a very strong statement. But I wanted to put it because I'm not the one who labeled this achievement to be revolutionary. It was Gary King, who doesn't even use graphs. Could you imagine that? From the depth of darkness, he recognized that there has been a revolution here. And I'll finish repeating my proverb, data science is a science of interpreting reality, not of summarizing data. If you take it with you, I have accomplished what I hoped for. And I will only thank you, thank my co-workers, my students. Then short commercial, the book of why is available. Actually, it's not available because it's out of stock, but I brought with me 10 copies. I'm willing to sign them to those who have patience to stand in line. And don't miss it, seriously. You have a gentle introduction to the revolution that I described to you here, being done. Okay, commercial done. I'll be happy to answer any questions.
Okay. You're taking in questions here.
No. Questions? Objections? Violent objections? I have to entice you.
Hi, my name is Christina Lerman. We actually spoke to you on Sunday at the concert, Daniel Pearl concert, Memorial concert.
Correct, yes, I remember.
And I got this feeling that you had some objection to natural experiments. So I wanted to give you a chance now to tell us what you think about the ability of natural experiments to discover causal connections in data.
Well, natural experiments are derivable from structural equations. If you have in your model variables that economists call exogenous, actually they don't know what they're talking about. Because you don't find two economists that agree on what endogeneity is. But assume that they know what they're talking about. It's something you can recognize. Then you can do more than what you can do without a discovery. Right? You don't need then, you can do with additional assumptions, such as monotonicity and satisfaction of the exclusion restrictions, you can get causal effect with a randomized experiment just based on this particular exogenous variable you discover. It's natural derivative of what I've been talking about. Okay. It is no need to make a big science out of natural experiment. If you have a model that justifies the conclusions that we're talking about, then use it. It's part of it.
But you need to know the model first.
Yeah. Okay. Oh, I mean, the nice thing is that there is a camp of economists that say we don't need a model. We just stipulate that the lottery conducted someplace in Massachusetts is a decent and faithful lottery, which means it was really randomized. Okay? Choosing people drafting people by the birthday, for instance, okay? It's unrelated to. This is another, we don't need the model. Well, in this case, you have enough information about a variable that was decided by randomized experiment, so incorporate it into your model. But you still need to have the exclusion restrictions. Exclusion, that the IV, the instrument, doesn't have direct effect over the outcome. You need to have that, okay? It's in the model, if you have a model. If not, you assume it you assume it away. By not writing a model, you make the model assumptions implicit. You're not running away from the need to have the conditions expressed or exist in the reality. Okay. And the additional one, and they are missing a lot because they're not having a model. For instance, you can have an instrument which is not a bad instrument, but can turn into legitimate instrument by condition on some covariates. What covariates would allow you to turn a bad instrument into a kosher instrument? That is a question that the graph can tell you right away. Chick-chack. But if you insist on ignoring a model, of not putting model explicitly, you will miss the opportunity. So that's my answer to the IV people, Imbens and company, and what's Angrist and Fischke.
All right, thank you.
And by the way, it doesn't have any testable implication. Yes, ordinary IV model doesn't have any testable implications in the data. Under certain conditions, like if you have a binary X, then it has. You have bounds. Again, what I'm displaying here is that you take the model seriously, you can get results that you would miss if you ignore it. We all know that. We're all scientists, right? If you ignore the equations of physics and you want to walk in the dark, then yes, you can get by. You will spend your time going around the lamppost. Somebody will hand you a cane once in a while, so you can make a couple of more steps, but that's not science. Science is putting your model explicitly and decide when you don't need a model. Only by taking models seriously, you learn the condition under which you can dispose of them.
From your position as an expert on statistics, I'm kind of curious of your opinion, if you have one, on efforts to popularize statistics and models in the news media on things like election forecasting, on sites like 538 or other places who are trying to communicate probabilities, uncertainties to the general public. Have you seen those things? Do you have an opinion of them? I'd love to hear it.
I've seen a lot of use and misuse of statistics, and I think it's good to train the public to think in terms of uncertainty, to appreciate the difficulty of interpreting, of dealing with uncertainty. But you have to keep on telling them that statistics is a one-dimensional universe in a reality which is two-dimensional. Actually, it's two-dimensional in a reality which is three-dimensional. The third dimension is causation. Is that engine, that liver that you have, okay? Which statistics totally ignores. They don't ignore it in their guts. Which means every author of a regression book have in mind that he or she really wants answer to causal effect question. What causes what? But it's taboo. So you cannot write the word causation in a regression book. You just write regression and keep your hidden desire in your guts. And you call it trends. You don't want causal effect. You just want a trend, okay? You're cheating yourself. You're writing books. Your students feel that you are not honest. And when you advertise things in the media, the public feel that you're not honest. That you really have to ask the question that you desire to estimate. You have to ask a question about cause and effect. So, and when you advertise that studies have shown. What was the studies? Were they randomized experiments? Did they have a model or they ignore the model? The public will be educated eventually, and desire and demand to get more information about the study. Who did it? And under what conditions? Have they, what guarantee of performance, of reputability they have? The study will be educated. One of the reasons I wrote this book is to educate the public. I call it democratization of common sense. Don't laugh. Common sense is such a precious commodity that, that everybody tries to hijack it. And unfortunately, statistics is not completely innocent of that. Even now in the area of causal inference, many people try to hijack it. So that I wrote the book of Why, in order for people to understand and what causal inference is about, what conditions are behind it, and how not to be lured by various advertisements. Oh, I have you. Thank you, thank you. You have a question? I love questions. If you don't believe, then don't talk. I mean, no. If we don't have any belief about the world in which we live, then the idea is really we cannot make a single step. If we don't have a theory that guarantees that I will continue to step here, I would be scared and I will just find shelter in my cubicles. But if you are a scientist and you have some claim and somebody actually pays your salary so that you can recommend something to a decision maker, okay, then you have responsibility to tell a decision maker, either fire me, I have no idea of what's going on, that's one way, or I say, I'm going to make some assumptions. But be aware, I give you a recommendation that are contingent upon those assumptions. But my assumptions are reasonable, plausible. The veracity of my recommendation is exactly the veracity of my assumption. You can take it or leave it. But I'm giving you a tremendous amount of information by saying that. If you believe those assumptions, then my recommendation ought to be taken seriously, as much as you believe my assumption. This is it's all I can say. This is a science. Going from assumptions to conclusions. In many cases, we indeed do not have any knowledge about our environment, in which we have to give up, I have to admit. If you put me into archaeology, and I have no idea of how to dig this village from the right or from the left, I say, I have no idea. I admit, fire me, and bye. What I don't agree, people talk and talk and talk about things that they could have done better. And this is to make assumptions, because they are guided by those assumptions. The only difference is they don't put them explicitly and mathematically. That is unforgivable, because the mathematics is available to you today. So keeping it in your mind and doing ordinary correlation while keeping it in your mind and not putting it explicitly, it leads you to mistakes and to missed opportunities.
So that would be all the questions we would be able to take for now here. But please, we have 10 copies of the Book of Why outside. So grab your book. It's one of my favorite books, so you have to read it if you're planning to work in AI or machine learning. Even if you're not working, please read the book. You're going to learn a lot. Make it your favorite bedtime read. Every day, sleep with it. Maybe you'll be the next person who'll be able to take us a bit ahead on the whole revolution of causal inference and to be able to think about intelligence in a new way. And Judea, would you be happy to take questions on the table as well?
About what?
So we're doing 10 signings right now, 10 signed copies.
Yeah.
Would you be happy to take in questions on the table if somebody has more questions?
But person X will make person X plus 1 weight.
Yeah.
I just made assumptions. Yeah, I'd be happy to take questions, but let's go ahead with the table. And let's see if I have any important phone calls.
Okay.
So what's the schedule?
So Sylvia will be taking you. She has your bag. She'll take you to the table, and
Okay.
then we do the signing.
Good. I'm there. I'm yours.
Okay. Here. Thank you again.